When stars die twice, the mystery of zombie stars. In the vast, unblinking darkness of space, stars tell the most captivating tales. Born in the violent collapse of molecular clouds, they spend their lives teetering between gravity's pull and nuclear fusion's might, and meet their end in cataclysmic explosions that scatter cosmic elements far and wide. For centuries, astronomers believed they had a clear understanding of a star's final act. Our sun, for instance, would expand into a red giant, shedding its outer layers until only a dense, Earth-sized core remained. A white dwarf, slowly cooling in the emptiness for eons. This was the accepted narrative, a peaceful, final rest. However, recent observations have hinted at something unsettling. Some white dwarfs, once considered lifeless, exhibit unexpected activity. They flare with renewed energy as if awakened from their supposed slumber, challenging our understanding of stellar evolution. These enigmatic objects are dubbed zombie stars. This phenomenon conflicts with the conventional view of star death. How can a celestial body, having exhausted its nuclear fuel and collapsed into a cold, inert state, suddenly reignite? The answer lies in the intricate interplay between theory and observation. White dwarfs, after all, are stellar remnants, their cores solidified carbon and oxygen, and their surfaces littered with elements forged during their final days. Yet, some emit light in peculiar ways, suggesting secondary violent events, a helium flash or an influx of material from a companion star. These aren't the expected slow, inevitable deaths, they're stories of resurrection, stars defying a singular fate. The mystery deepens when we consider the evidence. Telescopes have spotted white dwarfs in binary systems, feeding off material from neighboring stars, potentially triggering novas or supernovae. But what about those isolated ones? How do they find new life? The data is intriguing but incomplete, leaving gaps in our understanding. Quantum tunneling, rare core fluctuations, external forces like gravitational waves or magnetic fields, or even the influence of passing celestial bodies, could stir these dormant stars. Yet, despite our models and equations, the universe continues to astound us. The existence of zombie stars challenges our grasp on stellar longevity, cosmic chemistry, and perhaps even the fabric of time itself. If a star can die twice, what other secrets lie in the space between life and death, waiting to be unveiled? In the quiet hush between the stars, where time seems to stand still, the universe has unveiled a paradox that challenges our understanding of stellar fate. It begins with a flicker, a sudden burst of light from a white dwarf, a celestial body long considered to have reached its final, inert state. These intense yet fleeting flares are not the gradual dimming of a dying star, but the violent reignition of something thought extinguished. They whisper a mystery that has captivated astrophysicists worldwide. How can we be sure these stars are not simply dying, but experiencing a revival? The answer lies in our most advanced tools, telescopes that scrutinize the heavens with surgical precision. Instruments like the Hubble Space Telescope and the James Webb Space Telescope have uncovered anomalies that defy explanation. Binary systems containing white dwarfs, once believed to provide fuel through companion stars, now show flares from those thought to be solitary. Consider WD 115217, a white dwarf whose light spectrum reveals debris from a shattered planet orbiting it, forming a ghostly ring of dust. While remarkable, this discovery pales in comparison to the true anomaly. Stars flaring without any sign of accretion. Their light curves exhibit sudden spikes, defying models predicting gradual material buildup. These stars do not follow the expected path of slow, predictable death. Instead, they experience erratic, unpredictable pulses. The data is intriguing but fragmented. Some researchers attribute these flares to helium flashes, intense fusion bursts in the star's outer layers. Others propose magnetic instabilities or the influence of unseen companions. However, each proposed explanation leaves questions unanswered, as models struggle to replicate the frequency and intensity of observed events. It seems the universe delights in pushing beyond our defined boundaries. The timing of these renaissances adds another layer of intrigue. Some white dwarfs reignite after centuries, defying the millennia-long expectation for such events. How can a star's core, once believed frozen, awaken so suddenly? Possible answers involve quantum fluctuations in the star's structure or the subtle influence of gravitational waves from distant cosmic events. But these remain hypotheses, not proven facts. The implications for our understanding of the cosmos are profound. The life and death of stars are no longer linear, but intricate labyrinths, with each new observation opening a corridor and each theory offering a map. As we delve deeper, we realize how much remains unknown. The universe, in its infinite complexity, consistently challenges our certainties. We find ourselves at the precipice of mystery, armed with powerful instruments and theoretical models that struggle to keep pace with new data. These zombie stars pose a conundrum: anomalies or harbingers of profound truths about stellar evolution. If stars can die and rise again, what other hidden entities lurk in the cosmos' shadows, awaiting their moment in the light? In the silent, unyielding void between galaxies, where ancient stars' remnants linger like echoes of forgotten songs, a question persists: what forces can rekindle a dead star's flame? The answer is not singular, but a collection of theories and hypotheses, each offering a glimpse into the universe's surprising nature. The most well-understood explanation for a white dwarf's resurgence is the helium shell flash, a process both delicate and violent. Imagine a white dwarf as a layered cake: its core, a dense crystalline lattice of carbon and oxygen; its outer layers, a thin, tenuous shell of helium. Over millennia, this helium accumulates, compressed by gravity until it reaches a critical point. Then, in an act of cosmic defiance, the shell ignites, initiating a runaway fusion reaction. The result is a sudden, brilliant flare that can outshine entire galaxies for weeks. A final, fleeting glow from a star long since dead. Beyond this scenario, some white dwarfs reignite without visible accretion, their flares appearing inexplicably. Here, theories become more speculative. One possibility involves magnetic fields so powerful they distort space-time itself. Picture a white dwarf with an intense magnetic field channeling energy from the cosmic microwave background, drawing heat from the void and igniting fusion in its core. This is not merely theoretical but mathematically elegant, challenging our understanding of what's physically possible. Binary systems also pose an intriguing riddle. In these systems, material from a companion star can spiral onto the white dwarf, slowly building up mass. This process accretion can trigger a nova, a stellar explosion that expels accumulated matter. Yet, some flares occur in isolation with no discernible companion, leading to questions of unseen energy sources. Could gravitational waves from distant black hole mergers subtly affect dormant white dwarfs? The idea is captivating, though evidence remains scarce. Despite these theories, the universe continues to present riddles unsolved. Some flares exhibit such irregularity that they seem random, as if stars play a cosmic game of chance with physics itself. Could quantum tunneling, particles bypassing energy barriers, be the culprit? Or is there a more fundamental process at work, beyond our current stellar evolution understanding? The implications are profound. If these theories hold, star life and death become cyclical, intertwined with forces yet to be named. The universe, it appears, embraces reinvention, raising the possibility that even dead stars can rise again. Not as ghosts but as puzzles demanding solution. Thus, the question persists: if a star can die twice, what other secrets lurk in the silence between its flickers, awaiting our discovery? The implications of zombie stars have far-reaching consequences, disrupting established theories in astrophysics and prompting a reevaluation of cosmic evolution's fundamental nature. Historically, stellar life cycles were envisioned as straightforward birth, fusion, collapse, and eventual quiet decay. However, the existence of zombie stars challenges this linear narrative, suggesting that endings are not definitive, but rather transitional phases. If white dwarfs can reignite, does it follow that stellar death is a gateway to a more intricate cycle? This question remains unanswered, compelling scientists to re-examine their models. White dwarfs, remnants of star formation, play a crucial role in the universe's chemical evolution. Contrary to popular belief, they are not inactive, rather, they serve as crucibles, forging elements like iron, nickel, and heavier isotopes during flare-ups. If zombie stars can experience multiple reignitions, their impact on cosmic enrichment could be significantly greater than previously thought. This realization introduces a new chapter into the universe's elemental composition, one that includes repeated eruptions from stars once considered dead. Such a shift in understanding galactic chemistry suggests that the Milky Way's makeup may be shaped by dynamic processes beyond our current comprehension. The challenge extends to the models themselves. Current simulations of stellar evolution are based on assumptions regarding the finality of white dwarf states. The discovery of zombie stars raises questions about the completeness of these models, potentially missing crucial variables or even mechanisms entirely. Could quantum fluctuations, once deemed insignificant at astronomical scales, contribute to reigniting cores? Might gravitational ripples from distant black hole mergers stimulate dormant stars? These are questions that demand new mathematical equations, simulations, and a willingness to abandon traditional paradigms. The philosophical implications extend beyond science. If stars can die and be reborn, what does this say about time's nature in the cosmos? Does it suggest an endlessly recursive universe where the same forces govern galactic birth, rebirth, and the cycles of civilizations? The notion is profound. It challenges our understanding of life and death's place within the cosmic tapestry. If a star can rise from its ashes, what other hidden secrets await discovery in the realms between life and death? What phenomena, currently beyond the reach of our instruments, might be revealed? Answering these questions could not only revolutionize astrophysics, but also redefine humanity's position in the vast cosmos. In the grand theater of the cosmos, where time stretches across eons and silence echoes mightier than any explosion, the tale of zombie stars transforms from a scientific anomaly into a mirror, reflecting the universe's essence. We've progressed from understanding stellar decay as a predictable process to contemplating the unsettling possibility of their resurrection. Traditional astrophysics' rigid frameworks have given way to a complex labyrinth where the cosmos defies precise categorization. Despite our equations and observations, the greatest enigma may not reside within stars themselves, but in the profound questions they pose about our place in the vast, indifferent darkness. Consider this: if a star can die twice, what does it imply about the concept of endings? Historically, we've regarded death as an absolute conclusion, a final punctuation mark in existence's narrative. Yet, the universe, in its boundless ingenuity, challenges this notion. It presents us with cycles, not merely seasonal shifts or planetary orbits, but a cycle of life and death inherent to stars. Once deemed cold and inert, white dwarfs now symbolize resilience, their flickering flares hinting at energy's potential rebirth, even in seemingly empty spaces. What does this mean for us? Are we also bound by linearity's illusion? Could our endings, our deaths, hold the prospect of transformation, with echoes reverberating beyond their occurrence? The implications extend further still. If stars can be reborn, what does this say about the elements they forge? The iron within our blood and the carbon in our bones are not merely remnants of ancient supernovae, but fragments of a universe perpetually cycling between creation and renewal. The zombie star's repeated outbursts serve as a metaphor for cosmic processes. Nothing is truly lost, as even the remains of dying stars contribute to new worlds' birth. If the universe operates on a cycle, what does this signify for time's nature? Is it a unidirectional river or an intricate spiral, eternally returning to its source? Despite our advances, profound mysteries remain. Zombie stars' irregular flare patterns and unpredictable timing challenge our understanding of causality. They suggest a dance between chance and necessity, where the laws of physics are not absolute but malleable, influenced by forces yet to be identified. Could quantum fluctuations enabling particles to traverse energy barriers also awaken dead stars? Or might gravitational ripples from colliding black holes, traveling for eons, serve as catalysts for distant revivals? In the silence following each flare, a question lingers: if the universe is a cycle of death and rebirth, what does this imply about existence's purpose? Are we, as transient beings with fleeting consciousness, mere notes in a cosmic symphony, or do we play roles in a grander design? If stars can rise from their ashes, could civilizations one day emerge from their world's ruins? And if the cosmos is a tale of endless reinvention, what narratives are we crafting now, and which will endure long after our departure? The universe, with its vast, luminous expanse, offers no definitive answers. Instead, it presents us with questions, as bright as zombie stars' flares and as enduring as time cycles. Perhaps, ultimately, This is its most profound gift, the opportunity to wonder, to seek, and to find meaning not in answers but in the journey of asking these questions. What will you choose to believe?